Good day, fellow. Setsu is back. Today, fellow, we are going to do this concept of VSEPR theory. VSEPR theory. You see? Then we use this theory to predict the shapes of molecules. You see, we use this theory to predict the shapes of molecules. Then what does VSEPR stand for? V stands for valency, valence S for shell. Also have E, which stands for electrons, then P is pair, repulsion, you see? Then now what I'm going to do is I'm going to start with the first one. We have, I think, 7 of them, but I'm going to start with the first one. The first geometry that as a learner you must know. Also, I'm going to give it general formula. Do you understand? I'll also use some examples as I go by. Then the first geometry that we have, it's a linear. Whereby its general formula is given by x, let me say 2, where A, it's a central atom, where X, it's a terminal terminal atom. Do you understand? Then I'm going to use an example. Suppose if, let's say, I were to give you beryllium chloride like this, see, and ask you to draw its Lewis dot diagram, then how would you draw the structure of beryllium chloride? By now we know that beryllium, it is situated in group 2, meaning it's going to have 2 valency electrons like this. Then we have what? We have Be. So we have let me do it like this. We have Be and 2 Cl. We know that Cl, it exists in group number 17, which means it's going to have 7 electron in outermost energy level, but we have 2 of them like this. Understand? We have something like this. Then now what is going to happen? We can clearly see that this valency electron is going to pair with 1 of Be. Same applies, this valency electron is going to pair with the other electron of Cl. At the end of the day, we are going to get the structure which is like this. Let me erase here. We are going to get a structure which is like this. Be, let me say Be, then X dot, with an X, like this. We are going to get a situation which is like this. You see? then the geometrical structure of beryllium chloride will then be what now? It will be regarded as a linear. Because if we were to draw a structural formula of this given general formula, it will be like this. You see, like this. It is more similar to this one. Do you understand? It's like if I were to replace these two electrons with a bond, it will be a single bond like this. Same applies to these two electrons. Then I would have something like this. Do you understand? Then we can clearly see that beryllium chloride is going to form a geometrical shape which is known as linear. Do you understand? Then now let us consider the next one. We also have the second one, which is known as, let me erase here firstly. The second one, which is known as trigonal planar. It is given by AX3. See, its structural formula will be something like this. See, something like this. Then now let me just give you an example. Then the example that I'm going to give is boron trihydride. Boron trihydride like this. You see, we know that boron is in group number 13, which means it's going to have valency of electron 3, valence electron in outermost energy level. Then we are going to have something like this for boron. Let me do like this. Then how many H's do I have? 3 of them. Each we already know that it's going to have 1 valency, then 2, then 3, like this. You see? Then this valency is going to pair with this. Then this one is going to pair with this. Let me do like this. Then this one is going to pair with this. You see? At the end of the day, I'm going to have a structure which is like this now. CP. Oh, sorry. Let me use electrons first. Like this. Then X for H. Another. Then we then X like this for another H. A dot with another X. Then this is going to be our structure, the Lewis dot structure of boron trihydride. Then now if I were to replace these bonds with a line like this, that means I'm going to get a situation which is like this now. I'm going to get a situation which is like this. See, for this bond of CH, for this bond of CH, for this bond of CH, like this. Do you understand? Then at the end of the day, I have a similar structure to this one. Hence, we say that boron trihydride, it is regarded as what? Trigonal planar. Oh, sorry, its geometrical shape is going to be of trigonal planar. You see? Let's continue. We also have this one. The third one. Also have this one, which is known as, let me say the third one, which is known as tetrahedral, like this. It is given by AX4. Don't forget that A, it is a central atom, where X it is a terminal atom. You see? Then now, if I were to draw a structural formula to have something like this, like this. Do you understand? Something like this. Then now, an example that I can give to this one, it's methane, like this. You see, we know that the Lewis dot for carbon is given by, it's like this. It's so simple because it is situated in group number 14 with 4 electrons in outermost energy level. Then I have 4 H's, hydrogen the first one, the second one, the third one, the fourth one. See, then this one is going to pair with this is going to pair with this one is going to pair with this, the last one with that one. You see, my apology about the light. Then at the end of the day, I'm going to get the structure which is like this now. See, sorry, then the first hydrogen somewhere there, the second one somewhere here, then third one, the last one somewhere there. You see, then now I want to replace my bond with some lines. You see, let me replace these electrons, the paired electron, with a line like this, another one with a line, so another one with a line like this. You see, at the end of the day, I'm going to get a structure which is similar to this one. You see, then which is similar to this one. My apology about the light there. It's H over there. See, then I'm going to get a structure which is similar to this one. Then we say its geometrical shape, it is tetrahedral, like this. Now let us continue. We also have this one now, which is known as trigonal bipyramidal. It is given by AX5. Don't forget that this one is a central atom, X is a terminal atom. Then the example that we have here is phosphorus pentachloride. This one. You see? Pentachloride. Then now we know that phosphorus, it is situated in group number 15. You see? It is situated in group number 15. Somehow this one is going to have 5 electrons in outermost energy level, like this. See, 1, 2, 3, 4, 5. Then I have 5 Cl, like this. Let me write X1. Hopefully I will have enough space. First one plus the second one. See, like this. And I also have third one over here. Then okay, let me write another one somewhere here. Then the last one somewhere here. You see? Then one thing that you just need to know about phosphorus, it's an exception. Its valence electron, all of them, they have that ability to bond. See, that means phosphorus is going to use all of its valence electrons to pair with what? With each and every valence electron, especially this one, with its valence electron. Then at the end of the day, this one electron is going to pair with this one of phosphorus. Same applies. This one is going to pair with this one with this. Then here, this one is going to pair with this. And also this one again is going to pair with that one. You see, phosphorus has an ability to use all of its valence electron in order to form some bonds. Then at the end of the day, I'm going to get a structure which is like, oh, this one is going to be much complicated. But what I can do is, let me just erase almost everything so that I can write it nicely. That means I'm going to have something like this. P, don't forget, going to pair with the first Cl. You see, sorry, over here, like this. I'm also going to have another one over here. Yeah, it's going to be messy, this one, but I'll try my best to, like this. Then somewhere here, another one with an X. See, okay, 1 2 3 7. Okay, another one somewhere here. Ooh, it's messy, this one, like this. And the last one somewhere there, like this. You see, this is going to be our structure. Oh, my apology about that light. You see, my apology about that light. At the end of the day, if I were to replace this paired electron with some lines, I'm going to have something like this. P in the middle with 5 bonds. Then going to have Cl over there. Cl, Cl, Cl. You see, this is going to be our structure. Don't forget that its general formula was given by AX5, like this. You see, then if I were to include the valence electron for this one, I'll do like this. Do you understand? Like this. See, like this. Then now we have the structure of what? Of phosphorus pentachloride. Then let us continue. We also have this one. Okay, we also have the fifth one, which is known as octahedral. The word octa means 8. See, but in this form we are going to have AX6 like this. Then now don't forget that 8 is a central, then this one is a terminal. The example that we have in this regard is going to be sulfur hexafluoride, like this. You see, same applies. Sulfur is an exception, meaning it's going to use all of its valence electron in order to form bonds. You see, then we know that sulfur, it is situated in group number number 16. See, that means it's going to have 6 valency electrons in outermost energy level, like this. See, sulfur is going to use all of its valency electron. Same applies phosphorus, sulfur, both of them, they are exceptions. You see, they have that ability to use all of its valence electrons in order to form some bonds. Then we know that sulfur, for fluoride can be written in this format. Fluoride, like this. We have 7 in outermost energy level. See, valence electrons. Then now, what I'm going to do is, we are going to have 6 of this. We are going to have 6 of this, like this, plus another one. We are going to have 6 of this, see, plus another one over here. Then I don't have much space, let me erase this side. Going to have 6 of this, like this. How many? 5. Then lastly 6. You see, then I'm going to pair this with this one with that one. Then this one is going to pair with this. Then this is going to pair with this. Then I have 2. This one with this one, and this one with this one. You see, I'm going to use all of its valency to pair with that of fluoride. Then at the end of the day, I'm going to have a structure which look like this. Let me erase and draw. We have S somewhere here. Then it's going to pair with the first fluoride. 1, 2, 3, 5, 6, 7. Another one somewhere here. It's 1, 3, 4, 5, 6, 7. Another one, X, 6, 7. Another one, X, F, 1, 2, 5, 7. Another, how many do I have? 5. Okay, let me put somewhere here. See, F, like this. Lastly, I'm going to have it there. See, my F. U is going to be messy. See, then now if I were to replace this paired electron, I would have something like this. Let me draw the structure somewhere here. I'm going to have something like this. See, F, fluoride, then this is what I'm going to have now. If I were to include the valence electrons, it would look like this. Like this. See, like this. Now, do you understand? This is what I'm going to have for this one. You see, like this. The octahedral. Its geometrical shape is known as octahedral. Now, let us continue. We also have the geometrical shape which is known as bent. Some they call it an angular. See number 6, bent. Some they call it an angular. See, it is given by AX 2, where now we have, let's say, 2 lone pairs. See, this E stands for lone pairs. This one, the terminal atoms. This one, a central atom. Then, it's like if I have something like this. For an example, you see, I have 2 lone pairs. Then it will bend like this. Do you understand? These 2 lone pairs, they are going to cause these 2 terminals to bend like this. You see? Do you still remember for a linear we had a straight, more like a straight terminal like this, but look, on this one is more bent. You see? As for angular, it's going to look like this. An example that we do have on this one is H2O. You see, we know that oxygen is going to have 6 valency electron like this, plus 2 of hydrogen like this. You see, then this one is going to pair with this, then this one is going to pair with this. At the end of the day, this is the structure that we are going to have. Bear this in mind. In reality, these 2 lone pairs, they won't look like this. See, they won't look like this. We know that this one is going to pair with this. They won't look like this. You see, instead, they are going to be in this side. See, then they will cause this molecule now to bend a little bit like this. Do you understand? If now I were to remove the paired electrons, I'm going to get a structure which is like this. Do you understand? Which is like this. We call the geometrical molecule of H2O bent or an angular. Do you understand? Now we have the last one, which is known as trigonal pyramidal. That one is so simple. We have trigonal pyramidal. See, which is given by AX 3 with 1 lone pair. Something like this. If I were to draw a central atom, I'd have something like this with 1 lone pair. See, for this one we have ammonia, NH3. NH3. We know that N is going to have 5 valence electron. Then how many H's do we have? 3 of them, like this. See, this goes with this one with this, the last one with this. At the end of the day, the structure that we are going to get is going to look like this. Let me draw it here. I'm going to get something like this H somewhere here, another H somewhere here, another H somewhere here. You see? Same if I were to replace the paired electron, I would have a structure which is like this now. See, and over there, 2 lone pairs. We have a trigonal pyramidal. Its geometrical shape See, like this. Do you understand? Then now what I'm going to do is I'm going to do a little bit of a summary for you in order for us to see the geometrical shape and also the general formula. You see? Then now I'm going to make a summary of everything to see them all together. You see? Don't forget that we spoke of geometry, and also the general formula like this. You see? Then I said to you, number one, we had a linear. You see, a linear which is given by ax2. That one is so simple. Number two, we had a trigonal planar, which is given by ax3. Then number three, we have a tetrahedral, which is given by ax4. Then number four, we had a trigonal bipyramidal is given by ax5. Then number five, we had an octahedra, which is given by ax6. See? Then lastly, I can add now a band shape, which is given by, or an angular, don't forget, angular, which is given by ax2, e2. 7, we have a trigonal pyramidal. Oh, sorry over there. We have, let me try to squeeze it somewhere here. We have a trigonal pyramidal. See, something like this. ax3 with an electron. See? Then I also gave you an example. See? I also gave you some examples. Let me see examples. We said this one, it can be BeCl2, see, beryllium chloride. This one, it can be boron trihydride, like this. Then somewhere here we have methane. Then somewhere here we have pentane. So, oh sorry, phosphorus pentachloride, like this. Then we have sulfur hexafluoride. Then we have H2O, which is known as water, and NH3 is known as ammonia. Like this. This is a quick summary for you to understand this concept. I hope you enjoyed the lesson and see you next time.